Welcome to Mastering Data Infrastructure with Python and SQL for Manufacturing Engineers. In this course, we will learn how to build databases and process data using SQL and Python. The course is structured into 6 sections. In Section 1, we will cover the course objectives and give you an overview of data architecture. In Section 2, we will set up the development environment we'll be using throughout the course. Sections 3 and 4 focus on SQL, while Section 5 dives into ETL implementation using Python. Finally, in Section 6, we will demonstrate how to deploy your database to a cloud environment. Let's dive into Section 1. In this section, we will cover the course introduction, discuss the limitations of relying solely on Excel versus the necessity of databases, and learn the fundamental of database architecture. Next, let's look at the objectives of this course. In many business settings, it is common to manually cross-reference and process multiple Excel files. Since Excel data is often entered manually by humans, it frequently contains dirty data, such as inconsistent naming conventions, typos, or missing values. Furthermore, complex formulas and macros often become black boxes or siloed knowledge, meaning if the person in charge leaves, the entire workflow stops because no one else understands how it works. In this course, we will learn how to break away from these legacy methods and organize our data using SQL and Python. We will cover data aggregation and analysis using SQL, data transformation using Python, and how to automate routine tasks by building robust data pipelines. This course doesn't just teach generic SQL and programming concepts. We will focus on practical, real-world scenarios used in manufacturing and supply chain management. For instance, we will execute queries and write code based on specific themes like the hierarchical structure of a bill of materials and part procurement processes. Finally, let's go over the course flow and the tools we will be using. After explaining the basics of databases, we will get hands-on and process data using actual SQL and Python code. For the database, we will use SQLite. It requires no server setup and allows us to run SQL queries in a lightweight environment. For the coding environment, we will use Google Colab. This also requires no local setup. You can easily run queries and scripts with just a Google account. For cloud deployment, in the final section, we will use Amazon Web Service. Our hands-on approach prioritizes methods that are easy to set up and cost-effective, so you can focus on learning. Next, let's discuss the limitations of relying on Excel and why databases are necessary. Excel is used in many business environments. It is a flagship product from Microsoft that has been in use since the 1980s. It is estimated to have over 1 billion users worldwide, with more than 90% of the global companies using it. It has been a standard tool in the business world for decades. However, there is a phenomenon where people use Excel for tasks that go far beyond its intended purpose, sometimes creating complex document-like layouts or pseudo-applications that are difficult to maintain. While Excel is often treated as a universal tool that can do anything, it's important to understand that there are many areas where it falls short. Excel is excellent for viewing generic tabular data. For example, it's perfect for displaying sales figures and date in a 2-dimensional grid or viewing simple data formats like CSV files. Excel also includes calculation features like formulas and macros. By leveraging macros, it is technically possible to perform complex processing. Additionally, Excel has a rich built-in visualization tools. For business users, it offers sufficient functionality to calculate corporate KPI, profits, and create reports. On the other hand, Excel is not suitable for storing large-scale data. In enterprise systems, we often store terabytes or even petabytes of data. However, since Excel runs on a local personal computer, the data capacity is limited by that PC. It is also not suitable for use cases where many users need to edit simultaneously. Excel does not have built-in features for concurrency control or queuing. Furthermore, it cannot be used for processes that involve joining a large number of tables. While Excel is fine for individual use or small teams, it cannot be used for use cases where hundreds of users are editing simultaneously. Let's look in more detail at what Excel is doing under the hood. To begin with, the computers and business servers we use daily are composed of hardware components such as the CPU, memory, storage, input interfaces like keyboards and mice, and output interfaces like printers and monitors. Each part has a different role. The CPU is the component for compute processing. Excel's processing speed depends on the CPU's performance. Memory is an area for processing temporary data. It's often compared to the size of a workspace on a desk. If the workspace is large, you can process many tasks in parallel. Storage is a place to keep data for the long term, such as a hard disk. Knowing this architecture helps you understand why a system like Excel is ill-suited for editing multiple cells simultaneously, performing complex calculations, or storing massive amounts of data. Suppose you place an Excel file on a shared server and have multiple users edit it simultaneously. Strictly speaking, editing means sending a write request. Excel is composed of tables and cells. If requests are sent to the same file simultaneously, Excel becomes sluggish or conflicts occur, leading to a loss of data integrity. In standard systems, to prevent such conflicts, it is common to implement request ordering or concurrency control. Excel is not suitable for large-scale data processing. Generally, if you save tens of thousands of records in Excel, the processing becomes heavy. In a standard data analytics platform, it is common to decouple compute and storage. Data is saved in massive storage, and the system extracts only the necessary records for work. Also, servers and storage are set up in parallel, allowing the number of servers to scale according to the volume of requests. Since this separation does not happen in Excel, the moment you open the file, processing for the active table starts all at once. As a result, the file becomes slow and heavy. Also, Excel cannot handle operations that involve joining multiple files efficiently. In Excel, performance degrades as external references increase. For example, if you are performing reference operations like lookup across multiple Excel files, the system opens those multiple files in the background, consuming a significant amount of memory. Eventually, this exceeds the processing capacity limit. In a real analytics platform, you don't need to make all data active. The design allows you to extract the necessary data only when needed, reducing the load on the server. So far, we have explained the pros and the cons of Excel processing. In the next section, we will introduce how to actually design a database. Next, let's cover the fundamental of databases. First, let's look at the key points to consider in database design. When designing a database, we determine the necessary queries based on what kind of processing needs to occur. Requirements related to these functions and behaviors are called functional requirements. In a database context, these include CRUD operation, search and extraction conditions, aggregation methods, and transaction control. For example, a functional requirement might be we need to retrieve sales data for a specific product over a specific period. On the other hand, requirements unrelated to specific function, such as database performance, reliability, availability, security, maintainability, and cost, are called non-functional requirements. In the previous section, we discussed the weaknesses of Excel. While Excel is convenient with its rich formulas, macros, and visualization tools, it cannot process massive amounts of data at high speed. Since Excel runs primarily on a personal computer, its performance is limited by the specs of that PC. Let's dive deeper into database design points, specifically focusing on performance. The first is data volume. You need to consider the initial data size and how it will grow or shrink in the future. And this helps you decide how much storage is needed and whether you need a strategy to scale storage up or down. In enterprise systems, the data volume often reaches terabytes or petabytes. Next is the input and output rate. You must consider the frequency of reading from and writing to the disk. Naturally, systems with a high read and write frequency require higher spec disk. And next is the transactions. And this refers to the number of requests the system processes simultaneously. If you send 100 requests at once, the load on the database increases. In this case, you need to consider database parallel processing and network connection pooling and conflict avoidance. The reason Excel becomes heavy when multiple users edit it at once is that it is a product designed for personal use. Next is the response time. This is the time from sending a query until the result is returned. Naturally, upgrading server specs improves processing speed. However, you can also improve speed by optimizing the database design itself. Finally, the index strategy. An index is metadata used to search for data efficiently. Think of it like the index at the back of a book. You set indexes based on business requirements, such as frequently searching for specific data. For example, you might create an index to search based on product IDs or dates. Also, database performance improves if you upgrade server specs. However, higher specs mean higher costs. In general business, there are budget constraints, so we need to find the optimal balance between performance and cost. Next, let's discuss OLTP and OLAP. OLTP stands for Online Transaction Processing. These databases are designed to execute real-time transactions. This involves operations that insert, update, or delete data. In other words, operations that make changes to the data in the database. Generally, operations that modify data are heavy processes. Therefore, we try to keep these processes simple and limit them to specific roles. For online analytical processing, its purpose is to aggregate and analyze past data over a wide scope. It focuses primarily on read operations and does not modify data. On the other hand, it requires large-scale storage to hold massive amounts of historical data. Also, to efficiently aggregate this data, we use query languages like SQL and high-performance analytics platforms. Finally, let's cover primary databases and read replicas. As we have seen, databases have different roles. The primary database is the main database for write operations. Since it handles daily data entry, it cannot be allowed to stop. If you run heavy analytical queries on this primary database, the load increases, which can negatively impact daily operations. To prevent this, we prepare a separate read-only database called a read replica and execute analytical processes there. In the cloud world, it is a standard practice to separate the primary database and the read replica. Furthermore, if a failure occurs in the primary database, the read replica can be promoted to become the new primary database. There are other design considerations for databases. but we will cover the details through hands-on exercises in the following sections. Next, let's move on to Section 2, Setting up the Development Environment. In this section, I will introduce Google Colab and SQLite, the tools we will be using throughout this course. Also, in the hands-on part, I will introduce RobotX, which is the core theme we will use consistently in this course. First, let's look at Google Colab. Let me introduce Google Colab. In this course, we will use Google Colab to implement and test our Python and SQL. Google Colab adopts the Jupyter Notebook interface, which is an interactive execution environment. Jupyter Notebooks are the standard environment used in AI and data analysis. Since essential libraries for data analysis are pre-installed, environment setup is very easy. Also, Google Colab is basically free to use. You only need a Google account to get started. Google Colab has been a widely used tool since 2017. Its main feature is its interactive development environment. By interactive, I mean that you can see the execution results of your programming code immediately. In traditional programming, you often have to write long scripts, compile them, and then check the results. However, in an interactive environment, the results are reflected instantly. Google Colab is based on a project called Jupyter. The name Jupyter is actually derived from the initials of three programming languages, Julia, Python, and R. In the following chapters, I will demonstrate how to use Google Colab in practice. Next, let's talk about SQL and SQLite. First, let's briefly review the history of databases. The theory of relational databases was established in the 1970s by an IBM scientist named Edgar Codd. Later, the System R project started at IBM, and the relational databases were developed. In the 80s, commercialization progressed, and Oracle released the first commercial database. Also, SQL spread as the standard query language. In the 90s, with the spread of the Internet, online transaction databases became common. Then, in the 2000s, demand for more flexible databases rose, and a new type of database called NoSQL appeared. Next, let's introduce SQLite, which we will use in our hands-on exercises. SQLite is a lightweight relational database system that does not require server management. While common databases like MySQL and PostgreSQL run on servers, SQLite is serverless, meaning it doesn't need server administration. It functions by being directly embedded into the application. It requires no installation or complex configuration, so you can start using it immediately. SQLite is generally used for lightweight systems or development environments. In this course, we will also use SQLite for the hands-on parts. In relational databases, data is modeled in tables consisting of rows and columns. Each column records data of the same type. For example, this student table stores student IDs, names, and email addresses. The student ID consists of the three-digit number. Also, since the student ID is a key that uniquely identifies the student, duplicate keys are not allowed. Since some students may not have a middle name, we allow nulls. On the other hand, the first name and the last name do not allow nulls. For email addresses, we only allow formats combining strings and the @ symbol. In this way, it's common to set constraints on the database to ensure data integrity. These kinds of constraints are standardized by ANSI, the American National Standards Institute. Relational databases guarantee data integrity and consistency. Because of these characteristics, they are used in high reliability systems. Next, let me introduce RobotX, the subject we will use for the hands-on exercises in this course. First, let's talk about the BOM. A BOM, or Bill of Materials, is a list of parts, raw materials, and sub-assemblies required to manufacture a product. For example, a car consists of about 25,000 to 30,000 parts. The BOM also includes specifications for colors, destination countries, and the grades, and the special parts for cold regions. The BOM is the most critical core database in manufacturing. It is used across various fields such as production control, cost management, and inventory management. Parts have parent-child relationships, meaning raw materials go through multiple stages of assembly and processing to become intermediate products before reaching the final product. These relationships are also represented in the BOM. Here is an image of Robot X, the final product we will use in this course. Robot X consists of four main components. First, it has one right arm, it has no left arm, it has two legs. It also has one circuit board and one body. The right arm and the legs are treated as sub-assemblies. Here, we represent the components of Robot X in a tree structure. The components include sub-assemblies and parts. As I mentioned, the sub-assemblies are the right arm, legs, body, and the circuit board. Then there are the parts that make up each sub-assembly. The screws are common parts used across different assemblies. The number attached to each box represents the required quantity. For example, one Robot X requires one right arm. Furthermore, one right arm requires 3 motors and 12 screws. Next, let's look at the sample data we will use in this course. We have the item master, BOM table, inventory table, and purchasing price master. Broadly speaking, these are classified into master data and transaction data. Master data contains basic information that changes infrequently and is referenced commonly throughout the system. Transaction data contain business transaction information that is updated frequently. For example, part and supplier information is not updated daily, except during initial phases like design. On the other hand, factory inventory information is updated daily. Since transaction tables involve frequent updates, they need to support operations like writing, updating, and deleting. Master tables, in contrast, are designed primarily for reference or reading. As I will explain later, we will set a primary key for each table. And please note that I have intentionally included missing or incorrect data in these tables for learning purposes. This is the content of the item master. The item master defines the products, sub-assemblies, and the components. One key point here is the sensor at the bottom. Although the sensor is not a component of Robot X, it's mixed into the item master. I included this as a dummy record to demonstrate as an experiment later. When we join tables, we will see that this sensor disappears because it's not used in the robot. The BOM master is essentially the blueprint for building Robot X. Here, we define the relationship between parent parts and child parts, as well as the required quantities. For example, you can see that the screw is used in 3 places: the arm, the legs, and the body. Next is the purchasing cost master. This represents the price and condition for each supplier. A key point here is that the motor has 2 different prices. This represents a scenario where the part price changed over time. We will use this later when evaluating the asset value of inventory. Also, notice that the screw data contains 100 pieces, which is text, not just a number. We will use this to demonstrate data cleansing later. Finally, we have the inventory table. This represents the current stock information. We will use this table to explain table joins and inventory calculations. That covers the list of sample data we will use. Throughout the course, we will perform data processing on this data using SQL and Python. What is a Python library? It is a collection of pre-written Python code designed for specific functions or purposes. Think of Python libraries like the functions. They save developers the trouble of writing every single line of code from scratch. For example, writing code for complex statistical processing or machine learning from scratch would result in a massive amount of code. By importing a library, you can achieve this easily with just a few lines. The Python is one of the most popular programming languages. It is said to have over 10 million developers worldwide, and a vast number of libraries are available. In this course, we will use libraries necessary for database operations. There are several ways to interact with databases from Python, but cursors and pandas are the most common. A cursor executes SQL commands against the database. It handles results one row at a time. This method is often used when an application interacts with a database via an API. A cursor fetches data one row or in batches rather than loading everything into memory at once. Its key feature is memory efficiency. Pandas, on the other hand, is a data analysis library for Python. It loads data fetched from the database entirely into Python's memory and treats it as tabular data. Now, let's introduce the Python libraries we will be using in this hands-on session. First is Pandas. This is a popular open-source library used for data manipulation and analysis. It is specifically optimized for handling tabular data structures called data frames. It allows you to read and process data from various formats like CSV, Excel, and JSON. A data frame is a two-dimensional data structure consisting of rows and columns. It allows you to analyze data stored in a table format, similar to Excel or relational databases. By loading data into a data frame structure, processing becomes much more efficient. Another method for interacting with databases in Python is ORM. It stands for Object Relational Mapping. It is a technique that allows you to interact with the databases using object-oriented programming. It automatically converts your code into SQL in the background, making it very convenient. On the other hand, it can have the disadvantage of reduced performance when fetching related data. They often fetch unnecessary data and can struggle to efficiently fetch only the specific data required. Since our hands-on exercises involve hierarchical BOM data, we will not use an ORM. Instead, we will handle operations using pandas. Next, let's introduce SQLite tree and SQL alchemy. SQLite tree is a module included in Python's standard library. It is an interface for communicating with SQLite. SQL alchemy is a third-party library for database interaction. It primarily functions as an ORM and is designed to let you manipulate databases using object-oriented programming concepts. For your reference, I have listed here the common libraries used in the field of data analysis and machine learning. Libraries like Pandas and NumPy are used for data processing. Matplotlib and Seaborn are used for data visualization. Scikit-learn, TensorFlow, and PyTorch cover a wide range of processes, including building and training machine learning models. By importing these Python libraries, we can easily execute complex calculations. One great advantage of using cloud environments like Amazon Web Service is that these essential libraries are often pre-installed. This means users typically don't need to build the environment from scratch. We will be using these libraries throughout our hands-on session. So let's get started the first hands-on training. We are going to use the Google Colab. If you search for the Google Colab on Google, you will see the page like this. And open the new notebook and then going to this page. The specification is very simple. You type your code here and execute it, and the execution result displayed immediately below. And it's free to use. However, please note that if you are inactive for a certain period, generally about 90 to 120 minutes, the runtime will be disconnected and the past data may be deleted. Also, the maximum continuous connection time is approximately 12 hours. So now that you have opened it, and let me introduce some basic operation. First, you can change the name of the notebook here, and I recommend that's easy for you to manage, such as the sample hands-on. And regarding the file, you can save it to the Google Cloud and the Google Drive and download it to your local machine. So let's click on the operation to check. I will enter the command, for example, the print a simple string, the hello manufacturing data engineering, and if you enter the code directory here and click on the Shift plus Enter, and so the result is displayed immediately below. So next we will proceed with the setting of the library. In this course, we will use the libraries such as the pandas, the SQLite, and the SQL Alchemy. They are pre-installed in the Google Cloud by default, but we will import them just to be sure. The first, I'm gonna import the pandas and SQLite 3 and SQL Alchemy and the Shift plus Enter. And then when you press the Shift plus Enter, you will not see a visual result like before, except for the version print. But the library is imported internally, and I'm going to check the version of the pandas, the Shift plus Enter. And you then see the pandas version here. It shows that version 2.2.2 is installed. So next we will enter the slightly longer script. As I mentioned, the Google Cloud may reset the data if it hasn't been used for a while. Therefore, we execute this initialization script every time to create a new, clean data. Then we will import the library like the SQLite, and we also define the database file name with the factory.db, and if there are any incomplete file remaining from the previous section, and this script runs the cleaning up process to remove them. And then next we upload a CSV file. We will upload the BOM, the item list, and the other table. And then we rename the uploaded file and register them into the database. So when you run Shift plus Enter, choose the file and the button appear here. Please select the upload file from here. So once uploaded, you will see the message indicating that the table has been created and the environment construction is complete. And if you click on the folder icon on your left, you can see that the CSV files are listed here, and you can also upload the file directly from this pane. So finally, let's verify if the exists properly the execution and SQL query against the factory.db database we just created. I will copy and paste the SQL query directly here and against the factory database. And we will use the SQLite 3 library to establish the connection to the factory.db, and then we write the SQL query, the select from the M item to display all the record from the M item tab. Then we use the concept of the data frame to display. The shift plus enter. So you can see that table is displayed successfully. So this concludes the introduction to using the Google Colab, and we will continue to perform the SQL operation using the environment in the upcoming chapters. Next, we move on to section 3, database design. In this section, we'll cover the essentials of database design, ER diagrams, normalization, SQL, and DDL, composite primary keys, and foreign keys. And let's start with the ER diagrams. I will introduce ER diagrams. ER diagram stands for Entity Relationship Diagram, and it serves as a critical blueprint for databases. An entity represents an object that holds information. In a database, this corresponds to a table. It is usually represented by a rectangle. An attribute represents a specific data item possessed by the entity. In a database, this corresponds to a column. Attributes are listed inside the entity. A relationship represents the logical association between entities. It is represented by a line, and the symbols called cardinality are attached to that line. Cardinality defines a numerical relationship between occurrences of one entity and another. Common relationships include one-to-one, one-to-many, and many-to-many. In this course, I am using a library called GraphViz to render these diagrams, but please note there are several standard notation for cardinality. Our sample data is centered around the item master, which connects to other tables via one-to-many relationships. For example, a single item can be stored in multiple inventory locations, so this is represented as a one-to-many relationship. Now we are going to create an ER diagram using the Google Colab. You can just follow along with this section. I'll input the code directly here. Now we are using the open source library called the GraphViz, and this library allows us to write information that constitutes of the nodes and the edges. And first we create a dot object. Here we can specify the attribute for the dot object, such as setting the node shape to the box or specifying the color. In practice, these nodes represent the contents of our table. We define the 4 nodes to represent our table: the M underscore item, the T inventory, M purchase price, and M BOM. And finally, we define the relationship. We describe the relationship between the M item and T inventory, and the relationship between the M item and M purchase price, and similarly for the M BOM. And executing the drawing command and shift plus enter to show the ER diagram is generated here. Next is normalization. Database normalization refers to reducing data redundancy and maintaining data integrity. There are 3 stages of normalization: first, normal form; second, normal form; and third, normal form. Here, I will introduce normalization using a simple example. Here is a table consisting of a part manufacturer, place of manufacture, contact information, and so on. This table is not normalized, and there are multiple elements in one item. If normalization is not done, it will be difficult to maintain data integrity. It also makes it difficult to add, update, or otherwise process the data in the database system. I will normalize this table. The definition of the first normal form is that each column is atomic. The column does not contain multiple values. that the same column name is not duplicated in the same table, and that each row can be identified by a unique key. In the previous non-normalized table, the part manufacturer item and other attributes had a one-to-many relationship, but this relationship has been modified. Next, in the second normal form, in addition to the first normal form, a condition is added that the non-primary key column must be fully dependent on the entire primary key. This is called partial dependency elimination. In this case, the dependency is between the manufacturer, the place of manufacturing, and the contact information. In other words, the place and the contact information depend on the manufacturer. Additionally, the price and the number of products manufactured depend on the product. On the other hand, the product and date of manufacture depend on the manufacturer. This does not satisfy the second normal form. In addition, the third normal form has the condition of eliminating transitive dependencies, but there is a transitive relationship between the part manufacturer, the product, and the attributes related to it. To resolve this, the table needs to be split. Here is the table divided into two tables. It is divided into two tables, the manufacturer table and the product table. Finally, in the third normal form, the condition is that non-primary key columns do not depend on other non-primary key columns. In other words, transitive dependencies are eliminated. The tables in the second normal form are further divided and managed in three tables: the manufacturer's table, the products table, and the production table. In the manufacturer's table, the key manufacturer uniquely determines the place and the contact information. In the products table, the price is uniquely determined by the product name. As a side note, the manufacturers and the product tables are master tables, and the production table is a transaction table. The part manufacturers, their manufacturing locations, contact information, product names, and the prices do not change on a daily basis, but the production table changes daily. When designing an actual database system, transactional data should be designed to allow for frequent data updates. We are going to perform the normalization using the simple code. First, I will copy and paste the code to create a simple sample table. The sample table consists of the item code, the item name, the category, the location code, and the quantity. It contains the duplicate data such as the cleansing robot, then the product. We are intentionally using the unnormalized table here. And we define the df.t, and it contains the duplicate data. It creates the tabular data in the matrix format using the pandas. I will explain more about the data frame later in the course, but essentially they allow us to define the tabular data, which is similar to Excel. So let's display the sample table by pressing the Shift plus Enter. As I explained, you can see the duplicate data in the first and second row for the robot X, the cleaning the robot, and the product. And this means that the data is not normalized. Now let's normalize this data. We will execute the normalization process using the Python code. I'm going to paste the code here. And we define a new data frame with df underscore the item master. And we take the df.t to select the item code and item name and the category column, and use the drop duplicate function to discard the duplicate row, and clicking on the Shift plus Enter. So when we run this, we can get the data in a normalized form like this. and then we will cover the detail of the data frame later in the lecture. Next is SQL and DDL. I'm going to introduce what is SQL. SQL is a programming language for managing data in relational databases. It is used to retrieve, insert, update, and delete data in a database. There are several varieties of SQL which are standardized by ISO and ANSI. SQL is essentially one standardized language, but the database vendors add their own extensions, so a variety of dialects exist. Since this course focuses on SQLite, the explanation will be based on it. Just for reference, it can be pronounced as SQL or SQL. The SQL pronunciation is common in English-speaking countries due to SQL's origin from the term Structured English Query Language, SQL, of IBM. There are three types of SQL as described here. Starting in the next chapter, I will introduce the characteristics of each. DDL, Data Definition Language, is a language used to define, modify, and delete database structures. Specific commands include create, alter, drop, and truncate. Create is a command to create a new structure such as a database, table, or index. Alter modifies an existing database structure. A drop deletes a database, table, index, or other structure. A truncate deletes all rows from a table and empties the table. Here is a sample SQL command to create a simple table. In this example, it creates a table called Customers to hold customer information. The customer ID is set as the primary key, which must have a unique value. Last name and the first name are not allowed to be null because of the not null constraint. Null is allowed for all other fields. This SQL command will create an empty table. Actual data can be added to this table by executing an insert statement. Next, let's talk about primary keys. A primary key is a column or set of columns used to uniquely identify each record in a table. Primary keys have critical characteristics. First, values must not be duplicated across any rows in the table. Also, values must not be empty, null. Furthermore, there can be only one primary key per table. In our sample data, the part code in the item master acts as the primary key. Using the part code as an anchor, users can search for information related to that specific part. As I will introduce later, we sometimes combine multiple columns to create a composite primary key. In actual business practice, strictly defining uniqueness with a single attribute can be difficult, so we often execute queries by combining multiple elements. Also, in relational databases, we strictly define data types. In this course, we will use the strings for part codes and names, integers for part quantities, date types for order and inventory dates, and the decimal types for financial calculations. Relational databases strictly define not only the data type, but often the length, number of digits or characters as well. This prevents incorrect data from entering the system. Next, let's introduce composite primary keys. A composite primary key works by combining multiple columns to form a single key. By combining multiple elements, we guarantee uniqueness. In the previous section, I mentioned that you can set only one primary key per table. However, in actual business practice, it's often difficult to uniquely identify data using just a single column. For example, you might purchase the same part from multiple suppliers and need to manage their inventory separately. In this case, the information part A alone is not enough to uniquely identify the specific inventory record. Therefore, we combine the part code and the manufacturer code to set them as a composite key. Looking at the RobotX sample data, We need to set the composite primary key for the inventory table. For example, part A001 is manufactured by the two different suppliers, X123 and 1999. And if you search for unit price for the order quantity using only A001 as the key, you cannot distinguish which supplier manufactured it. And similarly, there are two records regarding to the B001. In this case, we need to combine the part code, supplier code, and the effective date to establish the composite primary key. And by setting the composite primary key in this way, we can uniquely identify the search for the attribute data. Next, let's talk about foreign keys. A foreign key is a special column used to logically link distinct tables together. By referencing the primary key of a parent table, it defines the parent-child relationship or association between the two tables. Foreign keys are usually established in tandem with foreign key constraints. This constraint restricts you from entering a value in the child table if that value does not already exist in the referenced parent table. In our specific case, we set the part code in the item master as the parent. All other child tables reference this part code. If you try to specify a part code in a child table that does not exist in the item master, an error will occur because it violates referential integrity. I will introduce the code we will use in the hands-on section. As I mentioned at the start, in this course, we will use Python libraries to execute SQL. SQLite3 is a standard Python library used to interact with SQLite. Let me explain how it operates. First, we establish a connection from Python to the database. We store the connection information in a variable named con, which stands for connection. When we modify the database and want to finalize those changes, we perform an operation called a commit. When we want to disconnect, we execute the close command. To execute queries against the database in SQLite, we generate an operator called a cursor while connected to the database. To issue commands to the database via SQL queries, we run cursor.execute. We use cursor.execute for a single query and a cursor.execute script when executing multiple queries at once. And next, here's the command for the manipulating the data frame using the pandas. To load the CSV file into the data frame, we use the read_CSV command, and the df is the standard abbreviation for the data frame. And to write the data frame to the database, we use toSQL, and this allows us to store the entire data frame in the database in one, and saving us the trouble with inserting the data row by row. We are going to the hands-on for the DDL, the composite primary key, and external key. First, we are going to create a table, and we will create the table using the create table syntax. And first, we will create the item master table, and then we create the inventory table as the second one. Copy and paste the long code So the first import the SQLite3. Although you may have already imported this in the previous section, I will repeat it because in the Google Cloud environment, the connection might be reset if you haven't operated it for a certain period. So just to be safe, I will import it every time. Then we import the SQLite3 library and then connect to the database. To connect, we define using the SQLite3.connect and specify the database name the factory.db inside the parents. So next we define the cursor. The actual SQL syntax is written in the red text here. We first drop the delete table if they were uploaded or created in the previous section, and we will temporarily delete the m underscore item, the item master, and the t underscore the inventory table. And after deleting them, we create the new m underscore item table using the create table. And for the item master, we set the item code, item name, and the category, and define the item code as the primary key. So we also define the not null constraint for the item code. And then we also use the create table to create a table named the T inventory. The inventory table has the item code, location code, and quantity, and we set the composite primary key using the both item code and the location code, and we set the item code as a foreign key. So now let's execute this. And to execute, we store the long create table SQL variable into the cursor.execute script, and we have the try and the except blocks here. And this is the exception handling to display the error content if any error occurs. Then we commit the changes and close the connection. So I will click Shift plus Enter. So the table has been created. So in the same way, and we will create the next table. Again, I will directly and copy and paste the code. So I will enter the import SQLite just in case and define the connection and the cursor. And here we write the SQL content inside the SQL create the price. Then we delete the M purchase price table, which we uploaded in the previous section, and recreate a new. The table contains the item code, the supplier code, the start date, end date, unit price, MOQ, and the read time. And here we set the three columns, the item code, supplier code, and the start date as the composite primary key. And we also set the item code as the foreign key, replacing the item code in the M item. Then we execute this, the Shift plus Enter to create the table. So next we will actually insert data into the table we just created to see if an error occurred. Similarly, I will copy and paste the code directly in the Google Chrome. So now we enter the three pieces of data. The first one is the normal data. We use the cursor.execute to directly enter the SQL command. We are inserting the data into the M purchase price, the table using the insert into. We are inputting the data for the item code, the supplier code, the start date, unit price, MOQ. And next we execute another insert. Here we have the same item code, the SCR M4, 10, and the supplier code, the supplier A, but the date is different. As a review, the M purchase price has the composite primary key set on the item code, the supplier code, and the start date. Therefore, the combination of these three columns serves as the unique key. Since the date is different, it is considered as a separate key, so no duplicate error will occur. But for the third piece of data, we use the SCR M410 supplier for and the 2023-0101 January 1st, and this is the complete duplicate of the first piece of data. So this data should cause an error. In this state, I will execute the command to check if the error occurs. So I'm gonna press enter. So as expected, the first record is registered normally. However, for the third record, an integrity error occurred just as expected. As the final table, we will create the BOM table again. I will copy and paste the code as is. So after declaring the import connection and the console, and we will use the SQL the create the BOM to create the BOM table. And first we delete the existing the drop table, and then recreate the MBOM with the create MBOM. For MBOM, we have the parent item code, the child item code, and the quantity as table item, and the primary keys are composite keys of the parent item code and the child item code. As for foreign key, the parent item code and the child item code to reference the item code and the item code in M item. Clicking on the shift plus enter. So now the fourth table, the MBOM has been created. So next we will proceed with the data loading. We assume that the CSV files are already uploaded. Okay, so they should exist within the file system here. If the CSV files are not present, please upload them again. You can re-upload by running the initialization command or by presenting the upload button here. So I will proceed with the data loading, assuming the CSV file are ready. I will copy and paste the code, the data uploading code. I imported the SQLite 3 and the pandas just in case. And here we have 4 commands like the df, the equal pd.read_csv. And these commands load the data from each CSV file, and we connect to the database again. And if existing the data remains, we replace it. When we run this, the data loading should complete immediately. Okay, finally, we will verify the data. Again, I copy and paste the command directly in the Google Cloud. So, for example, let's look at the top 5 rows of the M purchase price, and we execute the display the command with the shift plus enter. So you can see that the table is actually stored like this. So to summarize, we create the for table by setting that the create table via the DDL, configuring the composite primary key and setting the foreign key, and we load the data in the created table using the CSV file, and finally we verify that data. Next, we move on to section 4, a SQL for data extraction. In this section, we will cover DML, which is used to modify data. We will also introduce advanced SQL queries such as join operations, recursive queries, aggregation, inventory calculations, and window functions. Let's start with the basics of DML. DML, data manipulation language, is a language for manipulating data in a database. It performs operations such as inserting, updating, deleting, and retrieving data. Select retrieves and extracts data from a database. Insert is to add new data into a database table. Update modifies existing data in a table. Delete removes data from a table. Since DML is the language used most in database operations, I will introduce each of these commands with the specific examples on the following pages. First, here is a sample select statement. Select is usually used in conjunction with the from and where. The table name follows from, and the condition for data extraction follows where. This query retrieves information from the employees table for an employee whose department is sales. The asterisk in the select statement is used to retrieve all information from the employees table. As a point of reference, since an asterisk extracts all data, the process can take a long time if executed on a table with a large number of records. Therefore, it is generally recommended to extract data with more specific conditions. Next, this query retrieves the email addresses and the department names of employees whose department is sales from the employees table. The previous example had an asterisk after the select and retrieved all columns, but this sample focuses on just the email addresses and the department names. Next, the query selects the first name, last name, email address, and the department name of employees whose department is sales. It also includes the condition order by last name to sort the result by last name. Next is a sample query that joins two tables. In this query, join the projects table with the employees table and select the project ID and the project name, along with the project manager's email address and department. Here, the project manager is associated with the employees table via manager ID and ID. Shorten the project table to represent it as P and the employees table to represent it as E. Select the project ID and the project name from the projects table and the email address and the department from the employees table. As a join condition, the manager ID in the projects table must match the ID in the employees table. This is an example of an update statement. The update statement updates an existing row. This query updates the department of the row in the employees table where the ID is 1. The command SAT means to assign a new value to the department field. Next is the delete statement. This deletes rows by specifying a condition. The where clause deletes only the record with ID equals 1. For reference, if delete command is executed without specifying a condition in the where clause, all rows will be deleted. Finally, here is a sample insert statement. This insert statement adds an ID, name, email address, and the department to the employees table. You need to specify the actual values during the insert. Again, DMR is used for operations that add, delete, or update actual data in the database. The more transactions there are, the more writes and updates are made to the database, which increases the load. Therefore, it is a common practice to separate reads from writes when there are many transactions. CRUD is a conceptual acronym that summarizes the 4 basic functions of database operation. Almost all database applications are built upon a combination of these 4 operations. While CRUD refers to the concepts rather than specific SQL commands, the term is frequently used in database design context, so it is essential to know. A typical database anti-pattern is the full table scan. When you execute select all, the database attempts to retrieve every single piece of data. Consequently, this can become a major performance bottleneck. Since it transfers unnecessary data over the network, it consumes network bandwidth and increases memory usage on the client side. Furthermore, cloud services often charge based on the amount of data scanned or retrieved, so this drives up costs as well. when querying, always explicitly specify only the columns you actually need. We are going to perform a DML data manipulation language operation, so let's start from the Google Cloud notebook as usual. Since it has been a while since my last session, I will run the initialization script introduced in the previous chapter again and re-upload the CSV file, and then to confirm the four CSV files have been uploaded and proceed with the operation. In this section, using the DML, I'd like to add and update some data in the T inventory table. And I'm going to copy and paste the code directory here. Just to be safe, I will import the library and declare the connection command and the cursor command again. And then try the registered data, the insert command. And using the cursor.execute. So to try execute the insert into T inventory to input the item code, location code, and the quantity into the inventory table. And for the values, I am entering the LED red for the code, the WH01 for the location, and the 100 for the quantity. And then clicking on the Shift plus Enter. So next I want to select the data. Again, I copy and paste the code, and I use the pd.read SQL to select the T inventory. I want to extract and display the LED red item code that just inserted. Clicking on the Shift plus Enter. So as you can see, it is displayed, confirming that the data was successfully inserted and selected. And next I want to update this data. Again, I paste the code directly here. And inside the cursor.execute, I run the update T inventory and set quantity equal 95. I have changed the quantity from the 100 to 95, and in the where clause specify them called LED red and the location code as WH01, and then click on the Shift plus Enter. Okay, now that update is complete, check the content just to be sure. Using the pandas, the pd read SQL, select the T inventory and display the data. And then finally, since we will not using this LED red data anymore, I will delete it. So and copy and paste the code, delete here, and execute the delete from T inventory where the item code equal LED red. Then lastly, I will perform the verification step. They use the PD read SQL to select the T inventory, and since LED red has already been deleted and we expect nothing to display, and clicking on Shift plus Enter. So as you see, an empty table is shown here. So this concludes the explanation of DML operations. Next, let's talk about joins. In a previous lecture, I introduced normalization. Normalization eliminates data redundancy and improves integrity. However, depending on the design, this can lower performance or require join operations to view data side by side. In systems where performance is a priority, normalization becomes a trade-off with the search speed. Therefore, we sometimes intentionally perform denormalization, reverting normalized data back into a form that is easier to query. This is also a quick review of a previous lecture. A join operation refers to linking two or more tables using a common key to combine them into a single table. In this sample, the left and the right table are joined by the same ID. However, when joining tables where the IDs differ between the two, there are several ways to handle the join. First is the inner join. This joins and extracts only the data where the keys match in both tables. In this sample, the ID in the left table are 1, 2, 3, 4, and 5. The right side has 1, 2, 5, 6, and 8. The common ID are 1, 2, and 5. In this case, we extract and combine only that common data, and this is an inner join. Conversely, an outer join extracts rows even if they do not match the join condition. In other words, it joins the tables including data for all IDs. When doing this, data that does not exist is filled with a null. For example, since the left table has no data for ID 6 and 8, the project ID and the project name are replaced with a null. Since the right table has no data for IDs 3 and 4, the name and the department are replaced with null. We call this an outer join or full outer join. There are two types of outer joins depending on the direction, left outer join and right outer join. A left outer join displays all rows from the left table and joins data from the right table only if there is a match. Since the left table has IDs 1, 2, 3, 4, and 5, we extract the data for those IDs. Conversely, a right outer join displays all rows from the right table and joins data from the left table only if there is a match. Since the right table has IDs 1, 2, 5, 6, and 8, we extract the data for those IDs that covers join operations. Joins are often a stumbling block for SQL beginners. However, in real-world practice, there are many cases where you need to retrieve and combine necessary data from multiple tables. I encourage you to pause here and review these concepts once more. We will proceed with the hands-on session regarding the join operation. Since I am continuing from the previous section, I still have the full CSV file and the factory.db in my folder here. And if some time has passed and your data has disappeared, and please execute the initialization script again to recreate the database. So firstly, I will connect to the factory.db using the SQLite tree to connect. And then look at the data we are going to join. We want to join the item master, the M item, and the inventory table, the T inventory. There is a specific item called the sensor IR01. While this sensor part exists in the item master, but it doesn't exist in the inventory table. Let's verify this behavior by displaying the data. So, as explained before, performing the inner join, the only data common to both tables is extracted. Therefore, the sensor data will disappear. On the other hand, if we perform the outer join, all the data, including the non-matching one, will be displayed. Let's observe this behavior. First, we will execute the inner join. I will copy and paste the code. So inside the SQL statement, we select the item code, item name from the m.item, the alias as the I, the quantity from the T inventory, the alias as the imb. We perform the inner join linking them by item code. So the clicking on the Shift plus Enter. So as a result of inner join, the sensor data, the mentioned area, is not displayed here. Because the sensor data is not a common part shared between the inventory and item master table, it disappeared in the inner join. So next we will execute the left outer join. I will copy and paste the code. In the left join, we keep the entire left table, the item master, and extracting the matching data from the right table, inventory table. The syntax is similar to before, but we change the inner join to left join. So clicking on the Shift plus Enter. So now the sensor IR01, the sensor that disappeared area, is displayed in the outer join result. So finally, you can see that the quantity for the sensor is displayed the NaN, and not a number. We want to convert the null value into the appropriate value like a 0. And I will copy and paste the code. And this time we use the function called the serverless, which replaced the null value. Since the quantity contains the nulls, we replace them with 0 and rename the column to the quantity save. The rest of the syntax is the same as before, and clicking on Shift plus Enter, and you can see that the value has been replaced with 0. So this concludes the hands-on session on the behavior of inner and left joins. Next is recursive queries. Recursive queries are also a very difficult concept for SQL beginners. We will go through each step carefully using diagrams to help visualize the process. In a previous chapter, I introduced the BOM. A BOM represents the composition of parts in a hierarchical manner. For example, since a car consists of about 20,000 to 30,000 parts, the parent-child hierarchy can reach 7 or 8 levels deep. A BOM can be thought of as a hierarchical database. However, standard SQL finds it difficult to handle this kind of hierarchical data. For instance, if you join a parent-child hierarchy, you can query data one level down. If there are 7 levels, you would need to join tables 7 times. To avoid this kind of repetitive chain of joins, we use recursive queries. A recursive query is a SQL query that repeatedly executes itself while referencing its own result set within the database. It is used to traverse and manipulate the entire hierarchy when data in the table has a tree structure. In a recursive query, the initial result set that serves as the starting point is called the anchor member. In a BOM context, we specify the top of the hierarchy, like the final product. The recursive member is the target to be joined. It fetches data by referencing the previous level, moving to the next level, then the next. This process repeats until it reaches the final endpoint. Recursive queries use a temporary result set called the Common Table Expression CTE. Retrieving hierarchical data is achieved by using this common table expression. The results of the CTE are not physically saved to the disk. They are discarded as soon as the query execution is complete. They can't be used for persistent data management. It will be easier to understand with a concrete example, so I will introduce one on the next page and in the hands-on session. I will explain recursive queries using the RobotX example we are using in our hands-on exercises. The components of RobotX have a parent-child relationship involving sub-assemblies and parts. First, we create a table for the semi-finished products that are direct children of the product robot eggs. Next, we create a table for the parts that are children of those semi-finished products and join them. Here is the actual query. Starting from mbom, we use the where clause to extract only the rows where the parent item code matches the robot X. These extracted rows represent the direct parent-child relationships for robot X. Next, we select the parent item code as the root item, along with the child item code and quantity. Furthermore, we add a new column called level. This level represents the depth of the hierarchy. For the initial parent-child relationship, we set the level to 1. This is the table of the initial query result. We save this table with the name bomb3 as a temporary table, CTE. This temporary table is not saved permanently. It exists solely for this calculation. Next, we join this temporary table with the child hierarchy further down. Since they are the children of the children, we call this the grandchild level. We define the grandchild level as a level 2. The method for finding the grandchild level is the same as before. We search for the parents of the grandchildren from mbom. For example, right arm unit has children motor and screw. The query to search for grandchildren is expressed like this. Here, you can see the prefixes parent and child attached. We search for the parent from the temporary table bomb3 we just created. We search for the child from mbom. Regarding the quantity, it becomes the multiplication of the child level quantity and the grandchild level quantity. Finally, we connect the first query and the second query using the union or syntax. This is the final syntax of the recursive query. Recursive queries are among the most difficult syntax structures in SQL, so I hope you will learn each step while keeping the image of the parent-child relationship in mind. We are going to perform the hands-on exercise for the recursive query. Since I am continuing from the previous section, I will first check that the factory.db still remain in the folder, just to be safe. So then I will connect to the factory.db, use the SQLite 3.connect to establish the connection to the factory. So I will display the data from the mbom where the parent item code equal the robot X. As shown in the lecture, you can see the robot X as the parent code and its direct children listed here. So this output looks similar to the anchor member, the initial temporary table or bomb tree that we will use later. So now I'll input the long code directory and copy and paste it as is. And this is exactly same the syntax that the query showed in the lecture slide. So let's break it down. At the top, we define the bomb tree using the with recursive. The part here is called the anchor member. The initial member, inside the top query, we select the parent item code and set it as the root item, the leading item. And below that, we add the child item code, quantity, and this corresponds exactly to the direct parent-child relationship we displayed earlier. And this table becomes the base of the bomb tree. And we also add a column called the level to represent the hierarchy depth, initializing it at 1. And finally, we specify the where the parent item code equal robot X to create this temporary table. the bomb tree with the robotx as the root item. And the next is the recursive part. Here we select the root item, the child item call, and for the quantity. The me multiple by the parent's quantity by the child's quantity. And regarding the level, we add +1. Since the level defined in the anchor member was 1, the adding 1 makes the next hierarchy level 2. And then we perform the join operation. We join the bomb tree defined above with a table defined in the select statement from the mbomb. In the sample data for the robot X, a tree consists of the 3 generations, the parent, the child, and the grandchild. However, even if the continued for the 4, 5, or 6th generation, the syntax would not change. The recursive member repeats itself, and the level increments to the 2, 3, 4, and so on. The syntax allows us to execute a join operation repeatedly within a short piece of the code. And finally, let's display the result. Shift plus Enter. And this is the full bomb explosion list obtained through the recursive query. Next is aggregation. First, SQL function can be broadly divided into scalar function and aggregate function. The scalar functions return one result for a single row. They are used for relatively simple operations like string manipulation or numeric operations. Aggregate functions return one result for multiple rows. Common aggregate functions include count, sum, average, mean, and max. They perform calculations like adding up values from multiple rows or calculating their average. Spreadsheet software like Excel also provides similar formulas. Let's introduce some particularly important clauses related to aggregate functions. First is group by. The group by clause specifies which column to use for grouping the aggregation. For example, if we execute group by on customer ID in this table, it groups and aggregates the data for each identical customer ID. This table contains the customer IDs begin with the B, and the aggregation is performed for each of these customer IDs. In this sample code, we are calculating the sum. Next is having, a clause often used together with the group by. The having clause filters the aggregation results based on specific conditions. We group by customer ID using the same table as before. Against this grouped result, we specify a condition of 1000 or more using the having clause. As a result, only the group meets the condition of being 1000 or more. In the previous slide, I explained that having filters results based on conditions. However, SQL also has the where clause for filtering. When learning SQL, the difference between having and where is often cited as a confusing point. The where clause is used with the from and join. It is used to filter based on simple operations like scalar functions or individual rows. Having, as mentioned earlier, is used with the group by to filter the aggregated results of the groups. Now we will proceed with the aggregate function section. And this is a continuous of the previous section, so we assume the factory Davy exists in the folder. So as usual, we will establish the connection to the factory.davy using the SQLite. Click on the Shift plus Enter. So first we will execute the simple scalar function. Here you will be using the round function to perform the rounding, and we extract the only 5 rows and perform the calculation to display the the new column called the round price. Click on the shift plus enter. Okay, as you can see, the original unit price for each item code is displayed, but the decimal places have been rounded off in the rounded prices column. So for second sample, we will execute the aggregate function. I will copy and paste the code, and this sample calculated the count, the minimum, the max, and the average. From the unit price list, we are trying to count the supplier code and find the minimum, maximum, and average unit prices. So click on the shift plus enter. Okay, looking at the result, you can see the supplier count, the minimum price, the maximum price, and the average price displayed for each item code. In the query above, we specify the condition, the group by item code at the end. So therefore, the aggregation results are grouped and displayed by item code. So next, I would like to running this aggregate function without the group by clause, and I want to display the max price without the grouping, and copy and paste the code. So selecting the item code and the max unit price from the M purchase price without the group by. Shift plus enter. So as you can see, the unintended result is displayed. And what happened here? Although we are trying to display the item code in the select clause, but we are not grouping by item code. Therefore, the database treats the entire table as the aggregation target, and it extracts the maximum price from all data in the entire table. The item code displayed next to it is just the arbitrary value, often the first one found, and doesn't correspond to the maximum price. So I want to explore the result of the halving and the group by a bit more. So let's use another sample. I will copy and paste the code. So in this sample, we use both the group by and the where clause. So we are selecting the item code and the location code, and the sum of the quantity as the total quantity. And from the T inventory, the table conditions are where the filter location code to be WH01 and the grouping by item code, and having the filter aggregate the result where the sum quantity is 10 or more. So clicking on the shift plus enter. So the one piece of the data that meet all the conditions explained, the location, the WH01, and the total of the 15 is displayed here. The point here is the order of the execution when multiple conditions are present. In case, the order is the from, the where, the group by, and the having. So the from, where, group by, having, select. So next, let's see what happens if we remove some condition. The next sample code is the only having. We remove the where clause, which is limiting the location. And this means we are retrieving the data from all location code, not just WH01. And so the shift plus enter. Previously, the result was only the WH01, but this time, since we didn't filter the location, The result for the WH01 and WH02 are also returned, and this behavior is as expected. So let's retry the version with the only where and the no group by. I will express this to see the result. So click plus enter. Okay, and this result is an unintended state where the quantity of all the parts is summed up. In this code, we remove the group by and having and specify only where the location code equals the WH01. In this case, it displays the total sum of the all components in the WH01. In other words, the sum includes the screw, motors, and everything else mixed together. Even though we are not grouping, we are trying out to output the individual item codes. Therefore, behind the scene, the database displays the arbitrary item code hits the connection. For example, the first row. Consequently, the robot X is displayed, but the sum is for everything. To reiterate, if we look at the query with all conditions, where and having again, it evaluates the from, where, group by, having. And if you try to display the specific item code without group by, the result will be aggregated into a single value for the whole set, leading to the incorrect association. And finally, we want to execute the select the removing the both and where and having, essentially just the sum, is to try to calculate the total quantity of all the parts entire company. And I'm going to try the copy and paste the directory here and remove the where clause and shift plus enter, so that you can find the 367 is shown here. So in this case, it would again display the arbitrary item code and the location code alongside the grand total. Next, let's look at inventory calculation. We will apply the recursive queries and aggregate function we learned so far to implement inventory allocation logic using SQL. The general calculation flow is as follows. First, we perform a bomb explosion on the final product using a recursive query. This allows us to calculate the required quantity of components. Finally, we join the inventory table to calculate whether there is any stock shortage. Let's perform the bomb explosion for the final product, Robot X. As a refresher, here is the diagram of Robot X that I introduced in the previous lecture on recursive queries. Next involves calculating the required quantity of components. The key point in calculating a requirement is multiplying the parent part quantity by the child part quantity. For example, since there are 2 legs, the number of parts required for the legs is doubled. One leg consists of 2 motors and 8 screws. Therefore, if there are 2 legs, you need 4 motors and 16 screws. This is similar to car manufacturing, where you have 4 tires and the suspension is often symmetrical. Next, let's look at the screws, which are common parts. Screws are used in the right arm, the legs, and the body. A single robot requires a total of 34 screws. As a side note, in general manufacturing, commodity parts like bolts and nuts are often managed separately from other parts. It is common to order these generic parts in bulk, such as by the box. However, in this course, we will assume that screws are ordered individually. Next is the actual inventory calculation. If we were to produce 10 units of Robot X we would need parts for 10 units. In this case, the required number of screws would be 340. We join the inventory table with the requirements to cross-reference the current stock against the required quantity. Based on this, we calculate whether placing an order is necessary. That is the flow of the calculation. Next, we will actually implement the SQL query. For reference, I would like to mention time series inventory calculation. In this course, we are assuming spot production, where we make only 10 units of Robotex at one time. On the other hand, if we were to produce 10 units every day, we would need to incorporate the concept of time series inventory calculation. You would need to track inventory movement over time, 10 units on day 1, 20 units by day 2, and so on. In time series calculations, you must also consider procurement lead time, the time from order to delivery, and the safety stock. To perform this kind of calculation, you would need a separate time series database that holds data. Including time series elements in SQL makes the queries significantly more complex, exceeding the beginner to intermediate level. Therefore, in this hands-on section, we will focus on spot production. We are going to perform the inventory calculation hands-on. This is the continuation of the previous chapter, so I will proceed after confirming the factory.db still exists. And I will connect to the factory.db using the connection command. So the calculation can be executed using the single query structure. I will copy and paste the long code block here. The code is very long. It performs the calculation in the three main operations. The first, the block 1, is where we perform the bomb explosion. And this uses the exact same recursive query syntax introduced the previous lecture. By executing the recursive query, we are exploding the entire bomb structure. The differences from the previous time is that since we are making the 10 robots, we multiply the quantity by 10 to calculate the required amount, and we prepare the new variable called required quantity to represent the required quantity for 10 robots. And then the block 2 is for the aggregation. We create the new variable, the CTE, called the grouped leg. What are we doing in this calculation formula? As I mentioned before, some parts like the screw are used in the multiple sub-assemblies such as arms and legs. And here we group the required quantity for 10 robots, which we calculate the area, by component. By doing this, we calculate the total number of the parts required for Robot X and store in the final variable, the grouped leg. And this serves as the intermediate variable to group and display common parts by item code unit. For example, showing that we need, for example, 340 screws in total or 70 motor in total. And in the final, the block 3, we calculate the inventory allocation and the shortage. And this query is a bit long, so let's look at it from the bottom up. So you can see that we are performing the left join twice. First, we perform the left outer join with the M item, the item list. And next, we perform the left outer join with the T inventory, the inventory table. And therefore, we are joining the 3 tables twice, combining 3 tables into the 1 table. And we do this because we want to display the item name and the inventory quantity together. Against this joined table, we perform the select and execute the calculation in the rows below. And from the top, we display the child item code, the item code of the component, and the item name. And this item name is retrieved from the M item. And next, for the total rec quantity, we display the total required quantity calculated in the grouping block above. And we use the coalesce to calculate the current stock. If it is a null, we replace it with the 0, and then we display the shortage quantity. We calculate the final shortage by taking the total rec quantity and finally require the number per part, and the subtracting the inventory quantity, inv quantity using the coalesce. When I display this by presenting the shift plus enter, and we get the calculation result like this. The column displays the child item code, item name, and the calculated required quantity. For example, for motors, we need a total of 70 units. Then we have the current stock of the 15 units. And by subtracting the current stock, we find that the current shortage quantity is the 55 units. And looking at this calculation result, we know that for motors, since we are short by 55 units, we need to order 55 units. So this concludes the introduction to the inventory calculation query. Next, let's look at the window functions. Here, we will discuss how to handle cases where the unit price history changes. Generally, FIFO, first in, first out, is commonly used in inventory management. This means older stock is used first and newer stock is used later. The strictly managing the date of arrival is particularly important for products with expiration dates. In actual logistics operations, FIFO is strictly enforced. For this example, let's assume the unit price was 2,500 until March 31st and changed to 2,800 from April 1st onward. Let me introduce window function. A window function performs calculation across a set of related rows while retaining the original rows. The SQL syntax looks like this. First, the over declaration indicates that this is a window function. Next, partition by divides the data. For example, we can divide the calculation range by part code or supplier. Order by sorts the rows within that window. This sorting allows us to assign a rank or order. You can specify ascending or descending order. We will use window functions to assign an order to the fluctuating prices. Here is the execution result of the window function. To place a new order, we need the current price. Therefore, we use a window function to identify the record with the most recent start date from the past history data. To get the latest price, we add a new column using the window function and assign row numbers. We then extract only the data where the row number is 1. This allows us to calculate the new ordering cost. Now, let's talk about the inventory valuation. What we discussed so far was regarding ordering. In actual logistics operations, we often adopt FIFO using the older items first. Let's assume we ordered 10 units on March 31st, ordered an additional 10 units on April 1st, and consumed 5 units on April 2nd. This means as of April 2nd, we have 15 units in stock. In the case of the FIFO method, The inventory valuation amount as of April 2nd is calculated as shown here. On the other hand, in accounting, it is sometimes impossible to manage unit prices by tracking every single individual part. The valuation method used in physical logistics operation and the accounting system may differ. For inventory valuation, besides the strict individual FIFO, there are methods called the moving average method and the periodic average method, often referred to as weighted average. The moving average method calculates the average unit price every time new stock arrives. We calculate the average unit price as of April 2nd and multiply it by the inventory count to get the valuation. Since the valuation is calculated with every entry, the price fluctuations are smoothed out. However, system-wise, it requires an update operation for every single entry. The periodic average method determines the average unit price collectively at a specific point in time. And for example, the average price is determined during the monthly inventory stock take, and this method requires fewer calculations. For items like automotive engines, suspension systems, aircraft, or medical devices, where you need to strictly track when it was produced, the physical movement in the warehouse must match the system perfectly. In this case, the system also needs to manage additional data like lot numbers or timestamps. On the other hand, if you are not managing individual parts but managing them roughly, you apply an average unit price or latest unit price on the system for management. So now let's actually implement the window function of Google Colab. As usual, I am continuing from the previous section, so I will process after the confirming that the factory.db stream remain in the folder. And then I want to copy and paste the code directory here. Then I will connect the factory.db using the SQLite. So first I will display the data that will be subject of this query. Then I will use the pd.readSQL to retrieve the unit price for the motor, the MTR DC001 from the M purchase price table. So Shift plus Enter. So as we introduced in the lecture, the motor has two unit price, the 2500 and the 2800. We will use the window function to assign the ranking and process the data to use only the newer unit price of the 2800. So I will copy and paste the code directory. And then inside the query variable, the SQL rank, and I have put the select statement. Here we declare the over to use the window function. In partition by, we use the item code and the supplier code as a composite key to partition the data. And next we sort the data by the starting date in descending order, the newest first, and we assign the ranking based on this order and save it as the variable as the RN ranking. So clicking on the Shift plus Enter. So now you can see that the new column called the RN, the ranking, has been added to the history data shown earlier. And we want to retrieve only the newest ranking, which is number 1, since we sorted by the starting date. So the newest one is the rank 1, and the older one is the rank 2. So now we want to extract only the row where the ranking is 1 from this table. So I will copy and paste the code again. So inside the SQL lattice, we define the temporary table, the common table expression called the ranked price. The select statement inside this temporary table is exactly same as the previous one, the ranking syntax we used above. We create this table with the ranking temporarily, and then against this ranked price table, we extract only the data where the ranking is equal to 1. So click on the Shift plus Enter. So as you see, only the data with the ranking 1 is displayed here, and the data with the ranking 2 has disappeared. So this concludes the method for extracting only the latest price using the window functions. Next is section 5, implementing ETL and business logic. In this section, we will perform ETL processing on our data using Python. First, let's introduce ETL. ETL stands for extract, transform, and load. Extract refers to extracting data from various source systems such as databases and applications. Transform refers to converting that extracted data into a format suitable for the target system. This includes data cleaning, filtering, and aggregation. Load refers to loading the transformed data into the target system. By combining these three steps, we process data into its optimal form. Also, by automating this sequence as the data pipeline and scheduling it, we can process data with the minimal human intervention. I'm going to explain how ETL process is with easy example. The table shows a list of names, phone number, email, and age. John Doe is duplicated in the name field. In this case, you can choose whether to allow duplicates or eliminate duplicates. Phone number has to be numeric data type, but some characters are mixed in. There are some blank in the email addresses field. Some of the age field contains invalid numbers. When an irregular value is found, you will predefine rules and convert it to an appropriate format. In actual business, raw data often contains missing or irregular values. By processing these kind of data appropriately, the accuracy of data analysis can be improved. Here is the flow of the hands-on exercise we are about to do. In this hands-on, we will execute up to the extract phase of the ETL process. First, we will import pandas and SQLite 3, which we introduced earlier. Next, we will define the SQL queries to create the SQL tables we designed in the previous section. Finally, we will read the SQL tables into a pandas data frame. We will proceed with the data extraction hands-on. Since this is a continuation from the previous section, please verify that the factory.db database exists in the current folder. And if your session has timed out or the file is missing, please run the initialization script again. First, we will import the necessary library, and I'm going to copy and paste the code. I will import the SQLite 3 and pandas, abbreviating the pandas as PD, and then using the SQLite 3, and we connect to the factory.db, clicking on the Shift plus Enter. So next we will create the database table with the SQL query, and we are essentially defining the exact same query we created in the previous SQL question sections. But this time we are preparing them to be loaded into the data frames. And the first SQL statement, the SQL shortage, is the same one we created in the recursive query chapter. We execute the recursive query using the with recursive, the bomb tree. Assuming we are manufacturing 10 units of the robot X. We have added a calculation the quantity by 10 to determine the required quantity. And next, in the grouped rec CTE, we calculate the total required quantity for all child item codes. And finally, we perform the left join to create a data table that calculates the shortage quantity. Now I'm going to copy and paste and shift plus enter. And then the second SQL command is the SQL price is the one created in the previous lecture. It is the query for the price lift. We add the ranking to prices and retrieve only the data where the ranking is 1, and ensuring that we extract only the latest unit prices. So click Shift plus Enter. So now we input the SQL table defined into the pandas data frame, and we store the SQL shortage and the SQL price into the pandas data frame. Then I'm going to copy and paste the code and using the PD read SQL syntax. And to verify, we use the display function to show the top 5 rows of each data frame. So click Shift plus Enter. So we have confirmed that the SQL data has been successfully loaded into the data frame. So this concludes the hands-on session for the data extraction. Next, let's talk about data cleansing. Here is the purchasing price master table we will be cleansing in this hands-on. The data for screws contains 100 pieces, which includes non-numeric characters. If a cell that should contain a number holds text instead, it will cause an error during calculation. Therefore, we need to eliminate unnecessary strings. The purchasing price master is stored in the data frame named df price from the previous hands-on. Here is the workflow for this hands-on. First, we will remove non-numeric characters. In this case, the text 100 pieces is included, so we will remove pieces. Next, we will convert the data into a numeric type. First, here is the program code to remove non-numeric characters. The code is a bit long, but the part on the right is called method chaining. Method chaining is a technique in object-oriented programming like Python, where multiple method calls are connected continuously using dots. With method chaining, you can write a complex processing concisely in a single statement. In this code, the 3 methods are included. The first is the asType method. asType string declares that we treat the data type as a string. If the original data contains a mix of numbers and strings, processing might result in an error. In this case, for data like 100 pieces, we explicitly convert both 100 and pieces to strings. The second is .stat. This literally stands for string. To use the string manipulation functions like a regular expression in pandas, you need to attach this .str accessor. The third is replace. We will delete non-numeric characters. In other words, we replace anything that is not a number with an empty string. We also use regex or regular expression mode. Using regular expressions allows us to efficiently execute complex pattern searches, extractions, and replacements, rather than just simple text searches. Next is a process to convert to a numeric type. For conversion to numeric types, we use the function to numeric. We also specify coerce for error handling. This means we force the process. If there is a value that cannot be converted to a number, instead of stopping the program with an error, it treats it as a missing value. A fillna is a function to fill missing values. In this case, if there is a missing value, we fill it with 1. Finally, we use as a type integer to convert it to an integer value. We will proceed with the data transformation hands-on. We will start from where the previous data extraction hands-on ended, and we assume that the data frame, the DF shortage, and the DF price, which contain the SQL result, are already loaded. So first, let's look at the data before cleansing. I will print the DF price to display the item code and MOQ. So Shift plus Enter. So the MOQ stands for the minimum order quantity. Ideally, this should be a number, but as you can see, the text strings are mixed in with the data. We are going to remove these strings now. So next, copy and paste the formula that we explained in the lecture. So on the left side, we define a new variable, the MOQ cleaned, for the data after cleansing. On the right side, we take the MOQ clone and execute the function to replace the everything except the 0 to 9, the non-numeric character, with a blank string. So in other words, we leave only the number. So click Shift plus Enter, and then you can see the original string data in MOQ has been cleaned and stored in the MOQ value. So, but I intentionally include some tricky sample data here. There is an entity that say one box, the 500, but by simply removing the non-numeric character 1 and 500 get combined, resulting in the 1500. It's impossible for a system to perfectly cleanse such the inconsistent human entered data automatically. Therefore, we usually have to either write a more advanced query or include a manual data checking process. And if we were to write a query to extract the specific data, I will copy and paste the data here as the reference. And the code execute a query to extract only the 500 inside the bracket for the one box 500. So if I run this, so the 500 is extracted as expected. So finally, we will convert the cleaned data, which is string into the numeric type, and we will also handle the empty value with the NaN, the known value, by filling them with 1. So then we convert into the integer type. So clicking on the Shift plus Enter. So this concludes the flow for the data cleansing. Next, let's cover business logic. First, let me introduce NumPy. NumPy is a library for efficient numerical computation in Python. It is known as the de facto standard in fields like data science and machine learning. NumPy uses its own unique array data structure. Compared to standard Python lists, it can handle multi-dimensional data. This makes it widely used in fields requiring matrix operations such as machine learning and data analysis. In this course, we will use NumPy to calculate order lots and delivery dates. This allows us to process data easily by calling functions rather than writing long, complex code in SQL. Let's talk about lot production. There are several types of production methods in manufacturing. Besides producing items one by one like a car assembly line, there is a method called lot production or batch production, where items are produced in set quantities. In lot production, for example, if delivery is in units of 10, you cannot order in fractions. So even if you only need 5 parts, you must order at least 10. In this hands-on, the purchasing price master contains the MOQ, minimum order quantity. For example, screws are listed in units of 100, while motors are in units of 1. The minimum required order quantity is specified for each item. Also, we will use the datetime module to calculate the lead times. Datetime is a standard Python module for processing dates and times. In our sample data, the lead time from the supplier to the factory varies for each item. It takes several days from placing the order to actual delivery. We will proceed with the hands-on session. This is a continuation from the previous data cleansing session. In the previous session, we created the data frame, the DF shortage, and which contained the shortage quantity, the result of the SQL query, and the DF price, which contained the unit price. So first we will join these two tables, the data frame, using the pd.merge function. And this pd.merge function performs the same operation as the SQL join. I will copy and paste the code directly here and merge the df shortage and the df price using the left join with the item code as the key. And we will drop the rows where the price is missing, the NaN. So finally we keep and displays the only the necessary column, the item code, the shortage quantity, the MOQ num, and the read times date. So Shift plus Enter. So you can see the data is displayed like this. Next, we will import the NumPy. So I'm going to copy and paste the code, the import NumPy as the NP. And then we will execute the 4 logic steps at once to calculate the order quantity. I'm going to direct the copy and then paste the code directly here. So the first we will create the variable. We divide the shortage quantity by the MOQ num, the minimum order quantity. For example, if the shortage is 73 and the MOQ is 100, the result is 0.73. Next, we use the np.sale to round up this value. And once rounded up, we calculate the final order quantity. And finally, we convert the value back to the integer using the as type init and display it. So click Shift plus Enter. So looking at the result for the motor and the PCB, the shortage is 55 and the MOQ is 1, so the order quantity is 55. For the PCB, the shortage is 10 and MOQ is 5, so the order quantity becomes 10. So the next we will perform the calendar calculation with date logic. To calculate the date, we import the data time, which is the standard Python library, and Shift plus Enter. And then now we perform the calculation. So we add the read time to today, and we specify the unit as day. For example, if the read time is 3 days, it adds 3 days to the current date. And we also format it to the year, month, date to make it easier to read. And then display it. I'm going to Shift plus Enter. So for the motor, the lead time is 14 days. So it adds the 14 days to today's date to determine the delivery date. For the PCB, the lead time is also added and the delivery date is displayed here. So this concludes the introduction to the rounding logic and the lead time calculation. Finally, let's look at the load phase. In this step, we will write the result of our transformation into the database. By using the toSQL method, we can write the tabular data stored in the data frame directly into a SQL database. A key argument here is if exists. This argument checks whether the target table already exists and specifies the action to take. The fail raises an error if the table exists. The replace drops the existing table and recreates it from scratch. Append adds new rows to the existing table. We will proceed with the data loading section, and this is a continuation from the previous business logic section. First, we will load the data into the database. I will copy and paste the code directly here. And we use the df order .sql to define a new name, the t purchase order, and save data to the database. And we are saving the calculation result from the Python data frame we have worked on so far into the database. So clicking on the Shift plus Enter, and the database has been saved. And just to be sure, let's check if it was saved correctly. I will define the select statement to retrieve all the contents, the T purchase order. Then using the read SQL, I store the result of the select statement into the df verify. And when I display this, the df verify data frame, and you can see the entire picture of the table we created through the cleansing and business logic, and this confirms it has been saved as a database table. And for your reference, you can also output this data as a CSV file, not just to the database. I'm going to copy and paste the code. And regarding the CSV output, we used the df order.toCSV. We specify the CSV file name here. Click Shift plus Enter, and the message appears saying the CSV file output is complete. If we actually open the folder, we can confirm the CSV file named the purchase order has been created here. So this concludes the explanation of the data loading. Finally, we move on to section 6, deploying to the cloud. In this section, we will cover the features of database as a service, the basics of the cloud, and an explanation of Amazon RDS. Then we will proceed to create an account and do a hands-on exercise. Let me introduce the types of databases. Conventional table-type databases are called relational database and are generally known as Oracle or MySQL. A relatively new type of data format is called non-relational or NoSQL. NoSQL includes services such as key value, document, and graph types. Here is a list of databases provided by Amazon Web Service: Aurora, RDS, and Redshift as relational databases, DynamoDB as NoSQL, ElastiCache and MemoryDB as in-memory databases, DocumentDB is a document-oriented database, and so on. This slide shows the key points for database design that we discussed at the beginning. The SQL and the Python implementation we have covered so far falls under functional requirements. We built the necessary features and behaviors using SQL and Python based on actual business logic. On the other hand, the cloud deployment we are about to discuss requires us to focus mainly on non-functional requirements. Non-functional requirements refer to conditions related to quality and constraints, rather than the programming code itself. Specifically, these include performance, reliability, availability, security, operations and maintenance, and cost. We will select a database service while considering these non-functional requirements. I will describe the general benefits of migrating your database from on-premise to the cloud. A cloud databases offer fully managed support for patching servers, operating systems, and the database management systems, as well as backups and snapshots. In other words, customers do not need to manage infrastructure or servers. For example, on-premise, when a large number of requests are sent, the customer must manually build more servers. This requires a lot of overhead, but in the cloud, you don't have to worry about it. Also, it takes lots of time to update the version of the database management system. In terms of minimizing management overhead, it has an advantage over on-premise. You can easily create a high availability architecture. Imagine having physical servers in multiple locations on-premise. It requires a management overhead. You can build a master and a replica or master and a standby server with just a few clicks. If a failure occurs on the master, the standby server is automatically promoted to the master server. It also supports synchronous replication and automatic failover. In terms of performance, cloud database services support read replica. You can create read replicas across regions. In addition, it integrates with reporting and monitoring tools such as CloudWatch, CloudTrail, and Cloud Logging. It supports many security features such as encryption at rest and in transit, and access control, and the advantage of pay-as-you-go pricing. Next, I will introduce basics of cloud computing. First, I want to introduce the overview of cloud computing. The cloud computing is a model for delivering services to clients over a network, like the internet. Traditionally, the main approach was to have your own hardware in your own physical data center. But starting in the 2000s, it became possible to exchange software and data online, and this led to the development of the cloud. We call a physical data center that you manage yourself on premises. Setting up a physical on-premises server takes days or even weeks. Getting rid of unneeded servers is also difficult. Plus, physical servers require space, which increases your office costs. In contrast, the cloud lets you rent resources like servers and storage only when you need them, and only as much as you need. This makes deploying systems much faster. Since you pay on demand, you also optimize your costs. Next, let's talk about the cloud characteristic. We'll start with the availability. Availability is the percentage of the time a service is working. For example, the mission-critical systems in the finance or infrastructure must run the 24/7 and need extremely high availability. And to do this, you use the backup server, and if a disaster happens, the system switches to the backup server to keep the service running. Having a backup system for the failure is called redundancy. With redundancy, if one resource fails, the service continues on another, and this improves the availability. However, running the multiple server costs more. You typically define this in the service level agreement. And you should always design for the fault tolerance, meaning the system doesn't stop during the failure. You also need to design for the disaster recovery. Redundancy and disaster recovery work together to improve the availability. The geographic areas where AWS operates are called a region. Currently, AWS has 38 regions, and the number is growing up. For example, North America, including the US, Canada, and Mexico, have 11 regions. And inside each region, the data centers are grouped by the availability zones or AZ. Every region has the multiple AZ, and there are 120 total. For example, in the US East region, the North Virginia region has the 6 AZ. The actual data center locations are kept private for security. AZs are separated by the several kilometers, while regions are separated by the hundreds. This physical separation means if one location fails, another can take over. The placing the resources across the multiple AZ or region for redundancy is called the multi-AZ or multi-region architecture. If a disaster happens, we need a disaster recovery plans to continue the business. This provides a fault tolerance and a high availability. For recovery planning, we need two key metrics, the RPO, recovery point object, and RTO, recovery time object. RPO is the time since the last backup. It measures how much data you can afford to lose. For example, an RPO of the 12 hours means that you might lose 12 hours of the data. RTO is the time it takes to recover. It measures how quickly you must be back online. An RTO of 1 hour means you must recover within 1 hour. And generally, the shorter RPO and RTO value cost more. Next, let's talk about the scalability. The scalability is the ability to adjust your system performance or size based on demand. The scale up means increasing the power of the server. The scale out means adding more server. The opposite is also true. The scaling down makes the server less powerful, and the scale in reduces the number of the server. A key cloud advantage is that you can scale much faster than on-premise. You can also use the monitoring tool to set up the auto-scaling, which does this automatically. As a side note, we often call this the ability to automatically adjust resources elastic. This flexibility to change capacity is called elasticity. The concepts are very similar. Next, I'll talk about the pay-as-you-go pricing model. A pay-as-you-go is simple. You only pay for what you use. The moving to the cloud changes the capital expenditure, the CapEx, into the operational expenditure, the OpEx. And this means you change your fixed cost into variable cost. The buying the physical server is a large upfront investment, and for startup, using the cloud reduces these fixed costs and helping them become profitable sooner. The billing units differ by service, like the virtual machine, storage, or data transfer, and generally, the higher specs mean the higher price. The cloud cost benefit isn't only a pay-as-you-go. For example, you can reduce the staff cost for managing a data center or the rent for the building. You can also reduce the software license cost, and you can lower your overall purchasing and operational cost by using the cloud provider's economies of the scales. Next, I will introduce Amazon RDS. Amazon RDS is most general-purpose relational database service. When creating a database, you will configure a DB instance, which actually runs on compute resources on the cloud. For the database engine, it supports Amazon Aurora, MySQL, PostgreSQL, SQL Server, MariaDB, and Oracle. I'm going to introduce the elements of RDS. It offers multiple instance types like other computing services. Here is an example of the instance type notation. This table shows instance family of it. Instance families are categorized into general purpose and memory optimized types. In RDS, you can create a primary database and read replicas. The primary database handles general write and read operation, while read replicas are specialized for read processing. In the context of our hands-on exercises, heavy load queries, such as recursive queries, should be executed against the read replica to avoid impacting the main database. Although we won't cover them in detail in this course, I'd like to introduce some other key features. RDS supports multi-availability zone deployments, and this creates a primary instance and a standby replica in different availability zones within the same region. Data is replicated synchronously in real time. If a failure occurs in the primary DB, it automatically performs a failover to the standby environment. This typically allows for rapid recovery without the need for manual intervention. Regarding backups and restoration, it supports automated backups once a day with a retention period of up to 35 days. You can also take manual snapshots at any time, keeping up to 100 snapshots. It supports restoring data from backups and snapshots, as well as point-in-time recovery. However, if your RTO recovery time objective is less than 5 minutes, promoting a read replica to a primary instance may be faster than using point-in-time recovery. Restoring from a backup typically takes anywhere from a few minutes to tens of minutes. Since read replicas are synchronized with the primary instance in near real time, recovery can be much quicker. For your reference, I have summarized the major database services offered Amazon Web Service, Microsoft Azure, and Google Cloud by category. Although we are using Amazon in this course, other cloud providers offer similar database services. Furthermore, the concepts regarding cloud availability are comparable, and other providers offer similar features to ensure reliability. Next, I will introduce account creation. First, let's talk about the tools. AWS provides 3 fundamental interfaces for managing its services: the Management Console, the CLI, and the SDK. The Management Console, or the console, is a graphical, web-based interface for managing services. It's the main dashboard you use to access all service after creating an account. The CLI, command line interface, is a tool to manage services from a terminal. It uses an access key and a secret access key for authentication. AWS also offers a Cloud Shell, a browser-based CLI in the console that requires no local installation or setup. The SDK, Software Development Kit, is used to integrate services directly into your applications. AWS provides language-specific SDKs such as Python, Go, with libraries for making API calls from your code. Like the CLI, SDKs use an access key and a secret access key for authentication. This is a step to create a root account and IAM user. First, create a new account and then set up IAM user. IAM is a service that manages permission of users. First, search Amazon Web Service in your browser and go to the web page. You will see a button in the upper right corner that says Sign in to the console and click it. If you already have an account, you can sign in from this page. To create a new account, click Create a new AWS account. Enter your email address to authenticate your email. A verification email will then be sent to that email address. Next, enter your personal information such as address, credit card, phone number, etc. A credit card or debit card is required for your billing, even if your billing is 0. If you are not belong to a corporation and use AWS for personal development or just learning, I recommend you to choose the basic plan, which is free of charge. For developer plan and the business plan, you can get support from AWS customer engineers. Once you have completed this process, AWS account will be created successfully. This is a page called Management Console, and this will be the main page when you use the AWS resources from now on. Now, I'm going to configure IAM. The first account that's created is called a root user, and it will be a powerful account like administrator with access to your credit card. If the account is compromised, there is a security risk. Therefore, AWS recommends that you create an IAM user and sign in as an IAM user instead of using a root user normally. First, type IAM in the search window above and move to IAM's dashboard. This is the IAM dashboard. In the initial state, root user has MFA is marked with a red triangle. It is recommended that you install the token apps on your smart device, and next time you sign in as a root user, authenticate with MFA. Next, create an IAM user. The next time you sign in as usual, sign in as this IAM user. You should not sign in as the root user except when checking your credit account. Click on User in the left menu, then Add User. Set the username. Check the access key and the password field for the credential type. The access key is used for the API, CLI, and SDK, and the password is used to sign in to the management console. Select Attach Existing Policies directly and choose Administrator Access. This will give the IAM user all privileges except credit card access. The tags can be any text you like. Tags allow identification of IAM users. If you create multiple users in the future, you may set the tags to identify each user. After successfully creating a user, be sure to save the access key and the passwords that are displayed. You can also download this in CSV format. When you have done setup IAM, you will return to the console again, and I will briefly introduce you to the structure of the screen. From the menu bar above, you can move to the various management screens. You can return to the top page by clicking AWS logo on your left. Click on Services to see all the services offered by AWS by category. You can also register frequently used services as favorites. Click on the CLI logo to open CloudShell. By doing so, you can manage the command line from within your browser as well. Click on the bell mark to view various notifications. You can find out about events, changes, and incidents for the services you are operating. Click on the question logo to get support. The type of support available depends on the plan. For example, the basic plan allows ticket-based questions about fees, while technical support is available with the paid plans. By clicking on the gear-shaped logo, you can edit the language, the visual mode, and so on. This is a recently added feature. The menu bar configuration may change in the future. Next, click on the pull-down where the region name is listed to navigate to the AWS region. Northern Virginia is selected by default. Basically, by selecting a region that is close to where you want to deploy your services, you can access your resources with low latency. Also, the services deployed and the fees vary slightly by region. Since AWS is a US company, so releases are generally the earliest in the US region and are then after rolled out to other regions. Documentation and other information is also available in English for the latest services and is gradually being translated into other languages. Finally, you can check the account information you have created from the upper right corner of the console screen. Clicking on an organization will take you to the AWS Organization Service page, where you can view information about the organization you belong to. From here, you can also check your service quota and usage status and so on. If you need to access credit information, you will need to sign out of your IAM user and sign in as the root user. We are going to proceed with the Amazon RDS hands-on. In this hands-on, we will actually create the RDS daily instance on the AWS environment and execute queries against it later. I will be working between the AWS Management Console in my browser and the Google Cloud. The first type RDS in the search bar at the top and navigate to the RDS page. And you will see the various information on the dashboard. Clicking on the Create Database from the menu on the left bar, and so we are now the database creation page. And there are two options, the full configuration and the easy create. The easy create automatically applies the recommended settings, but since we want to configure the engine option ourselves, we will select the full configuration. For engine option, choose the PostgreSQL, and we will use the default engine version. And since this is for testing purpose, we want to use the simple settings without the multi-AZ to save the cost. Therefore, under the template, select the free tier, and this will set up the single instance configuration. And scrolling down, settings for the database identifier, you can name it anything. I will name it the Postgres. And thus master, the username is Postgres, and by default. And for the master password, and since this is for the hands-on demo, and I will simply type the password and confirm the master password. It wants that this is a weak password, but we will proceed with it, for this is just a demo. And scrolling down to the instance configuration, and since we select the free tier, the micro, the smallest size, is automatically selected. And scrolling down to for storage, and we will leave the default as they are. And scrolling down to connectivity, and we are not connecting from the EC2 instance, so leave that. And for VPC, the default VPC is selected. And this is for important. For public access, select yes, because we need to connect from the Google Cloud via the internet. And for the security group, the default one is selected. And however, we will need to edit this later to allow traffic, as the security group acts as the virtual firewall. And scrolling down to the availability zone, I will select the US East one. I am using the US one, the North Virginia region. You can select the zone appropriate for your region. So for the database authentication, scrolling down, keep the password authentication, and turn off the performance insight to save the resource, and scrolling down to the bottom, and finally clicking on the create a database. So it takes about 5 to 10 minutes to create a database, so I will stop the recording at the moment. So now that the primary instance has been created and the status is available, so let's create a lead replica. So since creating the read replica also takes a time, so we will start the process. So select the primary instance Postgres, and from the action menu, click on the create the read replica. And for the database identifier, I will name it the factory DB replica this time. And most of the settings mirror the primary instance, and the same instance, the same region, and the same storage capacity, and the single edit, select the single edit. And for the connectivity, make sure the public accessible, and scrolling down, the availability zone is the same as the primary instance, and scrolling down to I don't need the performance insight, I don't need the enhanced monitoring, and unchecked the maintenance, and clicking on the create read replica. And this will also take another 5 or 10 minutes, so I will stop the recording. So now both primary instance and the replica have been created, and we will use the primary for the writing and the replica for reading. So clicking on the instance name to view the details. So under the connectivity and the security tab, and you will find the endpoint, and copy this. Also note that the port number is 5432, and please copy the endpoint for both primary and the read replica to the notepad. For the security group, and by default, the security group virtual firewall doesn't allow the access from the Google Cloud. We need to allow traffic on port 5432. Click on the security group on new tab, and moving on to editing the default security group, and go to the inbound rule, and clicking on the edit inbound rule. And you need to add the rule with the custom TCP, the port number 5432, and technically it's best practice to allow only the specific IP of the Collabo instance. However, for simplicity, you can set the 0.0.0.0/, which means allows all. And for reference to find the specific IP address of Google Collabo, I'm going to moving on to the Google Collabo page, and then you can run the curl command to get the IP address, and copy and paste to here. So, and once you have updated the security group rule, and clicking on the save rule, so we are ready to connect. So let's go back to the Google Collabo. So we will import the necessary library, and we will define the connection. And I'm going to copy and paste the code, the directory here. Then we will import the library, the pandas, SQL Alchemy, the SQLite 3, and we define the username, the Postgres, the password, and the database name. And then we define the connection string for writer instance, the primary instance, and the reader replica. And using the endpoint you copied earlier, and then clicking on the Shift plus Enter. If the connection is successful, we proceed to data loading. Since the Collabo session might have discontinued, we need to ensure the source data exists, and we will read the data from the initialization script to the clicking on to re-upload the sample CSV file. So for the CSV file uploaded, and we will read the data from the local factory.db with this command, and then write it into the Amazon RDS primary instance, the writer instance. So Shift plus Enter. So the data is written to the primary. Since the RDS handles the replication synchronously or near real time, the data should be available in the read replica immediately. So let's verify by reading from the read replica. So I'm going to copy and paste the code directly here, and we are going to read the data from the read replica, and Shift plus Enter. So we can get the sample data here. So we successfully wrote to the primary instance and read from the replica, and this confirms that the Google Cloud and the AWS environment are fully connected. So finally, we will execute the full ETL workflow. We will run the heavy aggregation. So now I'm going to copy and paste the code, and this code is the exact same one with the previous lectures, the recursive bomb explosion and the ranking on the read replica to offload the primary database. So I'm going to Shift plus Enter. Okay, and we can get the result from the read replica. And next we perform the transform, the business logic in Python, and I'm going to copy and paste. And these are also same ones with the previous lectures. This includes the data cleansing, the merging, and the data calculation. So I'm going to execute with the Shift plus Enter. And so we can get the result. This is the exact same one with the previous lectures. So finally we load the result back into the primary database instance, and we must use the engine writer, and we cannot write to the read replica. So Shift plus Enter, and successfully completes the process. So that's all for the explanation that actually manipulates the Amazon RDS instance from the Google Cloud. So we're gonna cleaning up the resource, going back to the RDS page. Although we use the free tier for the primary instance, the read replicas may incur the small cost, and once you finish the hands-on, please make sure to delete the instance. First select the read replica and go to and delete and type delete me in the field to confirm the deletion, and select the primary instance and go to the action to the delete, and uncheck the snapshot and retain automate backup and confirm the message, and again to type the delete me, and then delete the instance. So this concludes the RDS hands-on session.